So we've seen what neural networks are. We've seen how to train them by gradient descent, and we've seen how to work out the gradient by backpropagation. Now what we want to do is scale up to bigger and more complex networks. And there's one insight that we're going to get a lot of mileage out of in doing that, which is that most of our operations, and in particular the operations that are most expensive to compute, are basic linear algebra operations like matrix multiplication. As an example, here is our familiar feed-forward neural network. So let's start at the bottom with the input. The first step we take is to take the input, multiply each of the inputs by its own weight in order to derive the values of the hidden layer and sum them all up. So that's a dot product, and the hidden layer is basically a collection before the nonlinearity is basically a collection of dot products, and a collection of dot products is nothing more than a matrix multiplication. So if we write the multiplication like this, we get these two matrices, well, one matrix and a vector. And if we multiply them, that's the first step of the first layer of our neural network. And then we just have to add the bias, which is basically we can see as a vector addition, and that gives us the hidden layer before the nonlinearities. We can also make the bias node explicitly one element of the vector, but practically it works out better if we separate this into one matrix multiplication and a vector addition. So then from the unactivated hidden layer to the activated hidden layer, we just apply element-wise the nonlinear function. So the sigmoid function is a scalar to scalar function, so we just apply that to every element of the vector k. And from that, the second layer is just another matrix multiplication and another bias addition, and that gives us the output of the neural network. Now, why is this such a helpful insight? Firstly, because it makes our notation a lot simpler. If we express the neural network, the feed-forward pass of the neural network, in terms of matrix multiplications, this one equation is all we need. And that's going to help us a lot as we move to more and more complicated neural networks. The second reason is computational complexity. If we look at this the pseudocode that we had in the last that we developed in the last lecture, what we can see is that this highlighted part here is the main computational bottleneck. This is going to take the longest time because here we have two nested for loops. So if we think of the input and the output as having the same size n, then this is a quadratic operation because we have two nested for loops of size n. And if we think of this as matrix multiplication, we can use the fact that matrix multiplication is highly parallelizable. So we can make somebody else implement a very efficient version of matrix multiplication. This becomes very, very efficient if we have access to a GPU. We don't have to do it ourselves so long as we can express what we want to do in matrix multiplications, implement it in a linear algebra library like NumPy, and then we're done. We call this process vectorizing, basically the idea of taking an algorithm that we have, expressing it as a sequence of linear algebra operations, trying to remove as many loops as we can. And we do this to make the notation simpler and to make the execution faster. Basically, in terms of vectors and matrices, the modules of our feed-forward neural network now look like this. And if you implement this in pseudocode, it looks like this. And if you do this in NumPy, it actually looks a lot like this. So what about the backward pass? Ideally, we want both the forward pass and the backward pass to be vectorized. So in the backward pass, we also want to get rid of these loops. But in order to do that, we need to see if there is something similar to the chain rule in terms of matrix operations, in terms of matrix multiplication. So the question is, can we do something like this? Can we take the derivative that we're interested in, the derivative of the loss over the whole weight matrix W, and break it up into smaller derivatives that are also matrices and vectors, which we can then combine perhaps by matrix multiplications instead of scalar multiplications. Note that we're abusing notation here a little bit. So we don't often use these differential symbols in combination with matrices and vectors so haphazardly. We'll go to a more precise notation later. For now, we're just sort of trying to illustrate the idea of what we're looking for. The answer is yes, we can do something like this. There are many treatments of vector derivatives and matrix derivatives, which all have their own version of the chain rule. So that sort of points in the right direction. This is probably something we can do. but there are some problems along the road. First, let's see how this kind of thing is normally done. Basically, if we have a function that takes a vector or a matrix or something consisting of a large number of scalars and outputs something else consisting of a large number of scalars, what we're looking for in all cases is the combination of all possible derivatives, all possible scalar derivatives. So for every input and every output, we have one partial derivative. We take all these partial derivatives together in one big bag, and then we try to arrange them in some logical manner. For instance, if we have a function from a 3-vector to a 2-vector, then we have 6 partial derivatives, one for every input by every output, and the result is very naturally arranged in a matrix. So here we arrange the outputs horizontally and the inputs vertically, and that allows us to sort of present all possible scalar derivatives, partial derivatives, in a matrix, and this matrix is called the Jacobian. So depending on what our input is and what our output is, we can sort of work out how many partial derivatives do we have and what's the most logical way to arrange them. And for a lot of things, we can sort of see, well, 2 vectors, the most logical way to arrange that is a matrix. Scalar to a matrix, the most logical way to arrange all the derivatives is a matrix, and so on. But once we get to a point where the most logical way to arrange it is a 3D shape, what we call a 3D tensor, we run into trouble. And this trouble we already run into with the kind of chain rule that we were looking for, which we see here in the last element. The local derivative there is the derivative of a vector with respect to a matrix. So the most natural way to arrange that would be in a 3 tensor. Now, why is that a problem? Well, if you remember the pseudocode, the way we actually computed the gradients for W was by a set of 2 nested loops. So that was a quadratic operation with quadratic memory use. If we now use a 3 tensor, suddenly we have cubic memory use and a cubic operation. We most probably, to fill this 3 tensor, we would need 3 loops. So this is not what we're looking for. We were hoping to make this more efficient, not slower. So in order to do this properly, we need to be a little bit more careful than just grabbing a chain rule and working out the local derivatives. And the start of that process is these 2 simplifying assumptions. And these hold for almost all of deep learning, and this is basically what allows us to do backpropagation in terms of tensors, matrices, and vectors so efficiently. The first one is that we always have a single scalar output. Whatever we compute, we have one output, which is a number. Not a matrix, not a vector, it has to be a number. We call that L because that's always our loss. The second assumption is that whenever we take a derivative or compute a gradient or do any kind of differentiation, it's always of L. It's always the derivative of L with respect to something else. So basically, in mathematical notation, this is always what we're looking for. It's always L over something else, where L is a scalar and the something else is any kind of tensor. It can be a vector, a matrix, can even be a 3 tensor, a 4 tensor, or a 5 tensor. So long as the thing we're taking the derivative of is a scalar. In other words, in the diagram we drew earlier, we are always in the leftmost column. The output of our function globally is always a number, and the input is always a 3 tensor. So we can very easily say that the derivative, the way we shape the derivative that we're interested in, is always the same shape as the thing we're taking the derivative over. Note that that doesn't mean that we can never learn neural networks that don't have a non-scalar output, because we're going to want to learn neural networks that produce images, that produce speech, that produce probability distributions. We can do all of this. Our model output can be anything, so long as on top of that model output, we put a second part of computation, the computation of our loss function, which takes the output and reduces it to a single number that expresses how well the model is done. This L over W that we're interested in, the derivative of the loss with respect to some parameter tensor W, we will call the gradient of L with respect to W. And this is a standard name that you see in any kind of multivariable calculus setting. And the most common symbol for that is this, an upside down triangle called nabla. The thing you're taking the derivative of is the argument of nabla, in this case L, and the thing you're taking the derivative with respect to is the subscript of nabla, in this case W. Now we will also make a non-standard assumption, which is that this gradient with respect to W has the same shape as W. And that's not standard because normally In vector calculus, the gradient is a vector, and if your normal vectors are column vectors, then your gradient is a row vector. It's the transpose of your normal vectors. This is very useful if you want to use the gradient as an operator, if you want to multiply things by the gradient. We never want to do that. We only ever want to subtract the gradient from something, as in gradient descent. So for our purposes, it's much easier to think of the gradient as having the same shape as the thing we are taking the gradient for, in this case w. This also means that for us the gradient isn't always a vector. The gradient can also be a matrix or a tensor, or even a scalar. So for instance, if w has 3 dimensions, is a 3 tensor, then we can take the derivative of L with respect to w, and the ijk element of that gradient is then simply the derivative of the loss, the scalar derivative of the loss with respect to wijk. Now, given all these assumptions, the standard notation is a little bit cumbersome for us, so we'll introduce some new notation. The reason why is that in the standard notation, the thing that takes pride of place, L, is always the same. We know it's always L, it never changes. And the thing that we're actually interested in, which is what we're taking the derivative for, is W, and that's relegated to the subscript. So that doesn't really work for us, so we introduce purely for these lectures the following notation. We take the actual object of interest, put it front and center, and we add the nabla as a kind of operator, something like a transpose or an inverse operator, and we throw away the L, because we know the derivative is always with respect to L. So this is how we will write what we call the gradient for W, which is actually the gradient of the loss with respect to W. And the same notation holds for vectors or for scalars. So with these tools and assumptions added to our tool belt, we can start thinking about tensor backpropagation. And the recipe we will follow is the following. We will work out the scalar derivative first and then vectorize. So in scalar terms, we always know what to do. In matrix calculus or vector calculus, things might get a little bit hairy. So I'll try to avoid that as much as possible. We'll stay in scalar calculus, and we'll use the multivariate chain rule to help us work out the scalar derivative. And then after all of this has been done, we apply the chain rule step by step. And after this scalar derivative has been worked out, then we will vectorize. So let's see what that looks like. Here is our the first step of our backpropagation. So we've computed a forward pass, received the loss, and now what we're looking for is the derivative, the gradient for y. That's the first step in our backpropagation. And we'll work out what the gradient for y is first in purely scalar terms, and then try to vectorize. So in scalar terms, the ith element of the gradient of y is the derivative of the loss over the ith element of y. So we start there. We fill in the definition of L, which is this sum. Note that in this example, we've generalized the last output to be a vector. Y is a vector in this case. So the loss just sums the loss over all the elements of the vector. So we get this sum. We can work the sum out of the gradient. So we now have the derivative of something to the power of 2. We can apply the chain rule to work that into 2 separate gradients. The first reduces to 2 times yk minus tk times the derivative of yk minus dk. And the factor on the right, we notice that that's almost always 0, except when k equals I. So in this sum, all of the terms are 0 except one, and that's the one where k equals I. So that term we can isolate, and the rest of the terms we can throw away. For that term, the factor on the right, the derivative becomes 1. So we end up with just 2 times yi minus ti. So we've gotten rid of all the differential symbols. So we've now worked out the scalar derivative for yi. And now we can vectorize. Now we want to take this formulation and figure out a way to compute the whole of y nabla in one go based on basic vector or matrix operations. So first we write down what this vector y nabla looks like, which is basically all of these elements of the vector under one another in a vector arrangement. And now we can see quite easily that this can be simply computed by taking the vector y, subtracting the vector t, and multiplying that element wise by 2. So now using this, we can take one step back in the computation graph and compute the derivative for our parameters. So we have the same situation. We're interested in v nabla for the whole matrix, the gradients for the whole matrix V, and we start with just a scalar derivative for just a single element. in this case Vij. So we're looking for the derivative of the loss over element Vij in this matrix. And this is where the multivariate chain rule comes in, because between the parameter Vij and the loss L, there are a bunch of value nodes, namely the elements of the vector y. And we won't solve this in matrix terms. We will simply treat this as a scalar derivative and apply the multivariate chain rule, which tells us this. The derivative of the loss with respect to Vij is equal to the sum over all these elements of y of the derivative of the loss with respect to yk times the derivative of yk with respect to Vij. That's just the multivariate chain rule we've already seen. Now the thing on the factor on the left in this sum, L over yk, we've already computed in the last slide. So we don't need to compute it again. We can just refer back to y nabla k, which we already have. So we'll just fill that in and keep it as is, and only work out the factor on the right, yk over Vij. So we fill in the definition of yk, which is simply this affine operation v times h plus c, and then the kth element of that operation. That's yk. So we want to stay in scalar terms, so we want to get rid of these matrix operations for now. So the kth element of this matrix multiplication and summation is, first of all, well, it's the kth element of one vector plus another vector, so it's the kth element of the first vector plus the kth element of the second vector, which gives us this formulation here. And then for the matrix multiplication, as you can see in the diagram, the kth element of the result of this matrix multiplied by this vector is the kth row of V, and the dot product of that with the vector H is the result that we're looking for. That's one number, and that's the kth element of the result of this matrix multiplication. And if we write down that dot product in scalar terms, we get this. It's a sum of L over the elements of the kth row of V times the elements L of H. And now we're back in writing everything in scalar terms. We have a purely scalar formula here. So the next step is to get rid of the ck, which is a constant. It doesn't affect the gradient, and to work the sum over L out of the derivative and to combine it with the sum over k. So we have two nested sums here over k and over L. And we can tell by the derivative that out of all these terms over k and L, all of them are 0, because for all of them vkl is a constant with respect to Vij, except one term where k is equal to I and L is equal to j. So we isolate that term by replacing all the k's with i's and all the l's with j's, and we get this. And in this derivative, we simply cross out the Vij's on both sides, and we are left with the hj. So after all that, what have we learned? That the gradient, or the derivative, scalar derivative for weight Vij, is the derivative for element yi times element hj. So now we vectorize. Now that we've worked out the scalar derivative, we vectorize. So we want to know, for the whole matrix V nabla, what does this look like? First, we fill in the definition of the matrix based on the scalar definition we've just derived. So the element ij of this matrix is the element I of y nabla and the element j of the vector h. And we can compute this matrix very simply by taking the outer product of y nabla, which we derived in the previous slide, and taking the outer product of y nabla and the vector h. Or in other words, we multiply y nabla by the transpose of the vector h, and that gives us a matrix V nabla, which contains all the right elements. So to recap, to work out a particular gradient x nabla for some x, we write down a scalar derivative of the loss over one particular element of x. We use the multivariate chain rule to sum over all outputs and to work out this gradient in scalar terms. And then we vectorize the computation of that gradient into some computation in terms of purely matrix products and vector operations. So to finish up the video, we'll simply compute our walk down the computation graph. Look first at h. H nabla is a vector. So we'll write down first the scalar derivative of hi nabla, which is the derivative of the loss over hi. We apply the multivariate chain rule. Note that v and h are both inputs in this computation graph to y, so we're still taking the multivariate chain rule for y, which looks like this. The left factor, L over yk, as before, we've computed already, so we'll just fill that in, and we'll focus on the right vector, yk over hi, which looks very similar to the way it did before, except now we're taking the derivative over hi. So we work out again the brackets, we get rid of this matrix multiplication, or rephrase it in terms of scalar operation. We work out the sum. This is where things get different. So we have a big sum here over k and l, but now we see that multiple terms of this sum are non-zero, which are namely all the elements where L is equal to I. So we end up with a sum over K that looks like this. So here actually the definition of HI nabla is a sum, because we're finished, we've gotten rid of all the differential symbols, is a sum over K of YK times WKI. So how do we vectorize this? Let's first write down the definition of the vector H nabla in terms of scalar symbols, which looks like this. So every element of the scalar is one of these sums. So here we have to be a little bit clever to work out how to vectorize this. But one way to do it is to first to expand the vector y into a matrix that has the same shape as W. So we multiply y nabla by a row vector of 1s, which expands it into something that has the same shape as W. Then we element-wise multiply, and the result of that we multiply by a column vector of 1s, which has the effect of summing over the row. And that's a sort of standard way of doing expansion and summing operations in linear algebra notation. If you were to practically implement this in NumPy, it would actually look something like this. You add to the gradient of y, so y nabla, you add what's called a singleton dimension. So we turn it into a matrix of 1 by n, and then by multiplying that matrix by another matrix through broadcasting, the y matrix is automatically expanded. We element-wise multiply both of them, and then we explicitly sum over one of the axes. So that's H nabla. K nabla is a little simpler. So now we are applying the multivariate chain rule for H. Note that we no longer have to worry about y, because we can simply see everything above H as one operation. So once we have H nabla, everything above H we can forget about. We start in scalar terms, so the ith element of k nabla is the derivative of the loss over ki. We apply the multivariate chain rule and fill in what we already know, which is the h that we worked out last time. And we're only interested in the factor on the right, which is hm over ki. We fill in the definition of hm, which is the sigmoid function applied to km. We note that, again, in this sum, all terms are 0 except for one, which is when I is equal to m. So we isolate that term and replace all the m's by I. And the derivative of sigma ki over ki is simply the derivative of ki. And we know a useful bit of information: the derivative of the sigmoid function is the sigmoid function times 1 minus the sigmoid function, as we saw already in previous lectures. So we can fill that in. So this gives us our scalar version of the derivative for ki. And we can fill in the values for the sigmoid function. We can actually fill in, because we already computed those in the forward pass, and they're equal. The sigmoid of ki is equal to the value of hi. So we can fill in those values. There's no need to recompute them. And this gives us our scalar definition of the derivative of ki. And this one's very easy to vectorize. So for the whole vector k nabla, we simply do element-wise multiplication. Well, we simply take the sum that we did in scalar terms and do everything that we did there element-wise. So element-wise multiplication and element-wise subtraction of a vector of 1s minus h gives us our vectorized version of the computation of k nabla. So one left, w, and here the process is very similar to what we saw already for v. We start with the scalar derivative. We're looking for the derivative of the loss with respect to the element ij of w. We apply the multivariate chain rule to take the derivative, to break the derivative up into the elements of k. The left factor we already know. The right factor we will work out. We fill in the definition of k, and we work it back to a scalar formulation of that particular scalar element of k, which means writing it in terms of a sum. We work out the sum so that we get two nested sums over m and l. We note that for all the terms in this sum, there is only one term which is non-zero, which is the term where I equals m and j equals l. And for that term, we can work out the derivative, which gives us this, namely that the derivative of the loss with respect to element ij of w is the ith element of k nabla times the jth element of the input vector x. And the matrix that has its elements so defined can be computed by taking the outer product of k nabla with x. So that brings us to the end of our backward pass, and we can now take these derivations of the gradients and put them into code. And this is what it looks like in pseudocode. So what we see here is, despite the fact that we had to do a lot of work on pen and paper, the actual amount of code we've written is very concise, and in these 5 lines we've captured the entire backpropagation algorithm for this one particular feed-forward neural network. So what have we learned? We've learned that the process of vectorizing makes our notation simpler and our computation faster. If we want to apply this process to the computation of a neural network, then vectorizing the forward pass is usually easy. And when it comes to vectorizing the backward pass, the trick is to work out the derivatives in scalar terms, accumulate according to the backpropagation algorithm, and then vectorize. In the last and final video of this lecture, we will look at the last step we can take to make the computer do the work of computing the gradient for us. Namely, keep in memory the computation graph so that we can fully automate the backpropagation process.